Welcome to this problem walkthrough. Today, we'll be exploring problem number 1240, tiling a rectangle with the fewest squares. This is an intriguing problem that challenges us to divide a given rectangle into the minimum number of square tiles. We'll discuss the problem, explore possible approaches, and break it down step by step. Let's dive in. In this problem, you are given a rectangle with dimensions nxm, and the objective is to cover the entire area of the rectangle using the fewest number of squares. These squares can have any side length, as long as they are integers. The key requirement is that the squares must completely cover the rectangle, meaning there should be no overlapping squares and no part of the rectangle left uncovered. You are expected to return the minimum number of squares needed to achieve this. The input consists of two integers, n and m, representing the dimensions of the rectangle and being the number of rows and m being the number of columns. The output is a single integer, which represents the minimum number of squares required to cover the rectangle. For example, if the input is n equals 2 and m equals 3, we'll see how to determine the output shortly. In the case where the rectangle dimensions are n equals 2 and m equals 3, the output is 3. This is because the 2x3 rectangle can be completely tiled using 3 squares of size 1x1. By placing these 3 1x1 squares strategically, we are able to fully cover the rectangle without leaving any gaps or having any overlaps. The solution is optimal, as it uses the smallest possible number of squares to cover the given area. Similarly, for a larger rectangle like n equals 5 and m equals 8, the output is 5, indicating the fewest number of squares required for that case. Let's look at how this result is achieved. For the rectangle with dimensions n equals 5 and m equals 8, the minimum number of squares required is 5. To achieve this, we can use a combination of larger and smaller squares. First, we place a single 5x5 square in the top left corner of the rectangle. This covers a significant portion of the area. The remaining area, which is a 5x3 rectangle, can then be tiled using 4 smaller squares of size 3x3. This arrangement ensures that the rectangle is fully covered while using only 5 squares in total. Now, for an even larger rectangle like n equals 11 and m equals 13, the problem becomes more complex, but the output is still a specific minimum value. When the rectangle dimensions are n equals 11 and m equals 13, the minimum number of squares required is 6. In this case, the solution involves using a combination of squares with varying side lengths to completely cover the area. Determining the exact arrangement of these squares requires calculating an optimal placement strategy, which minimizes the total number of squares used. The algorithm identifies the best configuration by exploring all possibilities, ensuring that the rectangle is efficiently tiled. The constraints of the problem help simplify the solution space, as both dimensions are relatively small. Additionally, certain edge cases like when n equals m or when one dimension is 1 are straightforward, as the rectangle either forms a perfect square or reduces to a line, respectively. The challenge in this problem lies in the vast number of possible ways to arrange squares within the rectangle, which can cause a combinatorial explosion of configurations. However, the constraints of 1 equals n, m equals 13 make this problem computationally manageable with the right approach. Techniques such as recursion with memoization or dynamic programming are well suited for this task, as they allow us to systematically explore and optimize the solution space. The goal is not just to cover the area but to do so with the absolute minimum number of squares. By leveraging these methods, we can efficiently solve the problem within the given constraints, ensuring optimal performance and correctness. To solve the problem of tiling a rectangle with the fewest squares, one approach we could consider is a brute force method using recursive backtracking. This involves starting with the entire rectangle and attempting to place a square in the top left corner. Once the square is placed, the algorithm recursively works on the remaining uncovered portion of the rectangle. At each step, it tracks the number of squares used and explores all possible placements to eventually determine the minimum required. The intuition behind this approach is that by exhaustively trying all configurations, we can guarantee finding the optimal solution. However, the downside is that the number of recursive calls grows exponentially with the dimensions of the rectangle, making this method computationally expensive and impractical for larger inputs. The sheer number of placements and backtracking steps leads to a worst-case time complexity that is exponential. To improve upon the brute force method, we can introduce optimizations like pruning and memoization. Pruning allows us to stop exploring any branch of the recursion where the number of squares placed so far already exceeds the current minimum. This eliminates unnecessary calculations. Memoization, on the other hand, ensures that we cache the results of previously solved subproblems, so we don't repeat work for the same input dimensions. Together, these techniques reduce the number of recursive calls and speed up the process significantly. Despite these optimizations, the method still struggles with high complexity for larger dimensions. Alternatively, we can consider a dynamic programming approach. In this strategy, the problem is broken into smaller subproblems, and we define dp, I, j, as the minimum number of squares needed to tile a rectangle of dimensions I x j. Using a recurrence relation, we evaluate all possible square sizes k x k where k is less than or equal to the smaller dimension of the rectangle. By placing a square, we divide the rectangle into smaller portions and solve for each iteratively, taking the minimum result over all valid square sizes. When using the dynamic programming approach, there are a few key observations that simplify the process. First, placing a kxk square divides the rectangle into up to 3 smaller subproblems, a strip above the square, a strip to the right, and potentially a smaller rectangle in the corner. Solving these subproblems systematically allows us to compute the minimum number of squares needed. Another observation is the symmetry of the rectangle. For instance, a rectangle with dimensions nxm is equivalent to one with dimensions mxn. This symmetry reduces redundant calculations, as we only need to compute results for one orientation. The time complexity of this approach is approximately n cubed * m cubed, since we compute dp, I, j, for all possible dimensions and evaluate all square sizes within each subproblem. Among the various strategies, the dynamic programming approach strikes a balance between optimality and efficiency. It avoids the redundancies of brute force while leveraging symmetry and memoization to keep the computations manageable, even though the complexity is still cubic in the worst case. This makes dp the most practical choice given the constraints of the problem. The breakthrough insight, or the aha moment, in solving this problem was realizing that dividing the rectangle into smaller subproblems based on square placement and leveraging symmetry could significantly reduce computational complexity. Instead of exploring every possible configuration like in brute force, the dynamic programming approach systematically considers all possibilities but avoids redundant calculations. By reusing results from previously solved dimensions and focusing only on unique configurations, this method transforms the problem into a more structured and efficient process. This insight ultimately led to a solution that balances optimality and practicality, making the dp formulation a powerful strategy for tackling this challenging tiling problem. Here, we're tasked with dividing an mxn rectangle into the minimum number of squares, ensuring that the entire area is covered without overlaps or gaps. To tackle this, we use a recursive backtracking approach, which systematically explores all possible placements of squares. The first step is to define the state. We represent the rectangle as a 2D grid, where each cell is either covered or uncovered, tracked using a Boolean mask. We also maintain a counter, current_count, to keep track of how many squares have been placed so far. The main idea is to use a recursive function to explore all configurations, starting with the top left uncovered cell and trying to place squares of different sizes, backtracking whenever a placement leads to an inefficient solution. The process begins with a base case. If all cells in the grid are covered, meaning no false values remain, then we consider the current_count as a possible solution. At each uncovered cell, we attempt to place a square, starting with the largest possible size that fits. For a square of side length k, we check two conditions: first, that the square fits within the bounds of the grid, and second, that all cells within the square are uncovered. If these conditions are met, we mark the corresponding cells as covered and recurse to the next uncovered cell, increasing the current_count. After exploring this path, we undo the placement by resetting the cells to their uncovered state, allowing the algorithm to consider other square sizes or placements. This backtracking ensures that all possibilities are explored. At each step, we iterate through all possible square sizes, starting with the largest and working down to the smallest. This ensures that we prioritize larger squares, which reduces the number of cells left to cover. To optimize further, we use pruning techniques to avoid redundant computations. For instance, if the current number of squares used exceeds the global minimum found so far, we terminate that branch immediately. Similarly, if a square size is too large to fit in the remaining uncovered area, we skip it. Edge cases are also handled explicitly. For example, if the rectangle has 0 dimensions, no squares are required. If it's already a perfect square, only one square is needed. And for thin rectangles, like 1xn grids, we know that only 1 by 1 squares are required to cover the entire area. There are a few key insights that make this algorithm work efficiently. First, placing the largest square possible at each step helps reduce the search space significantly, as it leaves fewer cells to cover. Second, recursive backtracking ensures that we explore all configurations, guaranteeing that we find the minimum number of squares. Third, pruning is critical for performance, as it allows us to skip unnecessary computations by terminating branches that are clearly suboptimal. Lastly, the state representation using a 2D grid and Boolean mask is efficient for checking covered cells and for undoing placements during backtracking, making the algorithm both flexible and robust. To implement this algorithm, we rely on a few key data structures. The grid, represented as a 2D array, is essential for tracking which cells are covered during the process. It allows us to efficiently validate square placements and undo them when backtracking. A global variable, min_squares, is used to record the minimum number of squares found so far, enabling pruning of suboptimal branches. Finally, the recursion itself relies on a stack either implicit through the call stack or explicit if using an iterative approach to manage the state of the grid and the placement of squares at each step. Analyzing the complexity, the time complexity in the worst case can be O, open parenthesis m times n close parenthesis squared, as we explore all possible square placements recursively. However, this is mitigated by pruning and by prioritizing the largest squares first. The space complexity is O, m*n, both for the grid representation and for the recursion stack. Let's look at an example with a 4x5 rectangle. Starting at the top left corner, we first attempt to place the largest square, a 4x4, but it doesn't fit. Then we try a 3x3 square, which is valid. After marking those cells, we move to the next uncovered cell and repeat this process until the entire grid is covered. Backtracking ensures that if a better solution is found, we update the result. For this example, the minimum number of squares required is 4. Here, we start by defining a class called solution and implementing the tiling rectangle method, which takes in the dimensions of the rectangle, m and n. To begin, we initialize self.result with the product of m and n, which represents the total area of the rectangle. This acts as an upper bound for the number of squares required, as the worst-case scenario would involve using 1 by 1 squares to cover the entire rectangle. Next, we define an array called heights, initialized to zeros, which keeps track of the current height of each column in the rectangle as we place squares. Within the implementation, we define a helper function called backtrack, which will recursively explore all possible ways to tile the rectangle. The first condition in this function checks if the maximum height of the columns equals m. If it does, it means the rectangle is fully covered, and we update self.result to the smaller value between the current result and the number of moves taken. This ensures we're always tracking the minimum moves. The second condition ensures we prune unnecessary branches. If the number of moves exceeds the current best result, there's no point in continuing down that path. Moving forward, we locate the leftmost column with the smallest height, storing its value in min height and its index in IDX. This is where we attempt to place the next square. The size of the largest square we can place is determined by the smaller value between the space left vertically in the rectangle and the space left horizontally from the current index. For each possible square size, starting from the largest and decreasing to the smallest, we simulate placing the square. This involves adding the square's size to the heights of the consecutive columns starting at the current index. By updating the heights array, we reflect the new state of the rectangle with this square placed. We then call the backtrack function recursively, passing moves +1, since placing this square counts as one additional move. After exploring this configuration, we undo the placement by subtracting the square's size from the respective columns in the heights array. This backtracking step is crucial, as it restores the state of the rectangle to what it was before the square was placed, allowing us to try other configurations. Finally, outside the helper function, we initiate the backtracking process by calling it with 0 moves. Once the recursion completes, we return self.result, which holds the minimum number of squares needed to tile the rectangle. This completes our implementation of the algorithm. Here, we begin implementing the solution in Java. First, we define a solution class with a private variable result to store the minimum number of moves found. The main function tiling rectangle takes the dimensions of the rectangle, m and n, as input. We initialize result with the area of the rectangle, which represents the worst-case scenario where each square is of size 1 by 1. Then, we create an heights array to track the current heights of each column in the rectangle. This helps us determine where we can place the next square. To explore the possible placements, we call the helper function backtrack, passing in the heights array, dimensions of the rectangle, and a counter for the number of moves. The backtracking function is designed to recursively explore all valid configurations. Inside backtrack, we first check if the maximum height in the heights array matches the rectangle's height, m. If it does, this indicates that the rectangle is completely covered, so we update result to the minimum of its current value and the number of moves taken. If the current number of moves already exceeds the best result found so far, we prune this branch of the recursion to save computation time. Next, we need to find the leftmost column with the minimum height, as this is the best place to start placing the next square. To do this, we initialize minHeight to a very large value and use a variable idx to track the index of the column with the minimum height. Now, we iterate through the heights array to identify the column with the smallest height. Once we find this column, we calculate the maximum size of the square that can be placed at this position. This is determined by taking the smaller of two values, the remaining height of the rectangle above this column, m minHeight, and the remaining width of the rectangle to the right of this column, n idx. After determining the maximum square size, we attempt to place squares of decreasing sizes, starting from the largest possible square for efficiency. For each square size, we update the heights array to reflect the placement by increasing the heights of the relevant columns. Then, we recursively call backtrack with the updated configuration and increment the move counter. After the recursive call, we backtrack by undoing the placement. This is done by decrementing the heights of the affected columns. This ensures that other configurations can be explored. By systematically trying all possible placements and pruning invalid or suboptimal paths, the algorithm ultimately finds the minimum number of squares required to tile the rectangle. To solve the problem of tiling a 2 by 3 rectangle with the fewest squares, we start by initializing the solution. First, self.result is set to 6, which is the product of m and n, serving as the initial upper bound. The heights array is initialized as 0, 0, 0, where each element represents the current height of the columns in the rectangle. The first backtracking call begins with moves equals 0. At this point, the minimum height in the heights array is 0, and the index of the leftmost column with this height is 0. The largest square that can be placed here is determined as min, 2 to 0, 3 to 0, which equals 2. A 2 by 2 square is placed in the rectangle, updating the heights array to 2, 2, 0. The algorithm then recurses, increasing the move count to 1. In the next call, the minimum height is still 0, but now at index 2. The largest possible square is min, 2 to 0, 3 to 2, which equals 1. This sets us up to place a smaller square next. A 1 by 1 square is placed at index 2, updating the heights array to 2, 2, 1. The algorithm now recurses with moves equals 2. In the subsequent backtrack call, the minimum height is 1 at index 2. The largest square that can fit at this position is min, 2 to 1, 3 to 2, which equals 1. Another 1 by 1 square is placed here, updating the heights array to 2, 2, 2. With this placement, the rectangle is fully tiled, as all columns reach the maximum height of 2. The base case is reached, and the algorithm updates self.result to the minimum of the current result, 6, and the move count, 3. This gives a final result of 3 for this example, meaning the rectangle can be tiled with 3 squares. Next, we tackle a 3 by 5 rectangle, starting with the initialization. Here, self.result is set to 15, and the heights array becomes 0, 0, 0, 0, 0. The first backtracking call begins with moves equals 0. The minimum height is 0 at index 0, and the largest square that can be placed is determined as min, 3 to 0, 5 to 0, which equals 3. A 3 by 3 square is placed in the rectangle, updating the heights array to 3, 3, 3, 0, 0. A recursive call is made with moves equals 1. In this next call, the minimum height is 0 at index 3. The largest square that can fit here is min, 3 to 0, 5 to 3, which equals 2. This sets the stage for placing a 2 by 2 square. A 2 by 2 square is placed at index 3, updating the heights array to 3, 3, 3, 2, 2. The algorithm recurses again with moves equals 2. In the next backtracking call, the minimum height is now 2 at index 3. The largest square that can fit here is min, 3 to 2, 5 to 3, which equals 1. Two 1 by 1 squares are placed to fill the remaining gaps, updating the heights array to 3, 3, 3, 3, 3. At this point, the rectangle is fully tiled, as all columns reach the maximum height of 3. The base case is reached, and the algorithm updates self.result to the minimum of 15 and 4, resulting in a final output of 4 for this example. Finally, we consider a 4 by 4 rectangle. We start by initializing self.result to 16, and the heights array is set to 0, 0, 0, 0. The first backtracking call begins with moves equals 0. The minimum height is 0 at index 0, and the largest square that can be placed is min, 4 to 0, 4 to 0, which equals 4. A 4 by 4 square is placed, updating the heights array to 4, 4, 4, 4. Since the rectangle is now fully tiled, the base case is immediately reached. The algorithm updates self.result to the minimum of 16 and 1, resulting in a final output of 1 for this example. This demonstrates the efficiency of using a single large square to tile a perfect square rectangle. To understand the time complexity of this solution, let's start with the backtracking approach and its components. First, finding the leftmost column with the smallest height is crucial for determining where to place the next square. To do this, we scan the heights array, which has a size of n, and finding the minimum height and its index takes n time. Next, determining the maximum size of the square that can be placed involves a simple calculation based on the remaining height and width of the rectangle. This calculation is constant time, or O1. When we place a square of a certain size, we update the heights array for up to size columns, which costs O size. Similarly, undoing the placement to backtrack and restore the previous state also takes O size. These operations are key to the algorithm's efficiency as we explore possible arrangements. Now, let's dive deeper into the recursive exploration process. The algorithm attempts to place squares of all possible sizes, starting from the largest size that fits and going down to size 1. This means that each state can have up to max size recursive calls, where max size is the smaller of m and n. The overall recursion tree is bounded by the number of unique states of the heights array. Since the heights array has n entries, and each entry can take values from 0 to m, the total number of states is O, open parenthesis m plus 1 close parenthesis to the power of n. For each state, the algorithm performs up to min, m, n, recursive calls, and within each call, it spends O, n, time for operations such as finding the minimum height and updating the heights array. Combining these factors, the overall time complexity is approximately O, open parenthesis m plus 1 close parenthesis to the power of n asterisk min, m, n, asterisk n. Let's analyze the space complexity now. The algorithm uses the heights array to represent the current heights of the rectangle's columns, which requires O, n, space since there are n columns. Additionally, the recursion stack depth is bounded by the total number of moves, which in the worst case equals the total number of tiles in the rectangle, or m asterisk n. This means that the recursive stack requires O, m asterisk n, space. Apart from these, the algorithm uses a few scalar variables like min height, idx, and max size, which take O, 1, space. When we combine these components, the total space complexity is O, n plus m asterisk n, which simplifies to O, m asterisk n, because the m asterisk n term dominates in the worst case. Let's compare the current approach to a brute force method. A naive brute force algorithm would generate all possible placements of squares in the rectangle, leading to an exponential number of states and making the solution computationally infeasible. However, the current approach optimizes this by incorporating several key techniques. First, pruning ensures that unnecessary branches are not explored. For example, when the number of moves already exceeds the current best result. Second, the use of the heights array allows the algorithm to efficiently represent the state and avoid redundant recomputation. Third, exploring square sizes in decreasing order prioritizes larger squares, which often leads to faster convergence. In terms of best, average, and worst cases, the best case occurs when the rectangle is already a square, allowing the algorithm to terminate quickly with minimal complexity. The worst case arises when the dimensions m and n are highly disproportionate, resulting in the maximum number of recursive states. On average, the pruning and state representation make the solution far more efficient than brute force. Finally, let's justify the big O complexity mathematically. The exponential term O, open parenthesis m plus 1 close parenthesis to the power of n, comes from the fact that the heights array has n entries, and each entry can independently take on values from 0 to m. This represents the total number of possible states the algorithm may encounter. The O, min is m, n, factor accounts for the number of square sizes that are explored at each state, as we try all possible square sizes from the largest to the smallest. Lastly, the O, n, factor arises from operations such as finding the minimum height and updating the heights array during placement and backtracking. Putting these together, the overall time complexity becomes O, open parenthesis m plus 1 close parenthesis to the power of n asterisk min, m, n, asterisk n, which reflects the interplay between the state space, the recursive exploration, and the cost of operations at each step. When tackling algorithmic problems, it's essential to avoid some of the most common mistakes that often trip up candidates. First, neglecting edge cases can lead to failures in scenarios you might not anticipate. For example, what happens if the input is empty, or there's only one element in an array? Always ensure your solution accounts for these edge cases. Next, while brute force is a reasonable starting point for smaller inputs, it becomes impractical as input sizes grow. Consider a naive O, n cubed, solution. It might work for small n, but it will time out for constraints like n equals 100,000. Also, the problem's constraints are a valuable guide. They can hint at the required efficiency of your approach. For instance, if n is very small, backtracking might be feasible, but if n is large, you'll likely need an approach like O, n log n. Additionally, recursion errors are another pitfall. Missing or incorrect base cases can result in infinite loops or incorrect results. Finally, watch out for off-by-one errors, especially with indexing. These small mistakes are incredibly common, so double-check your boundaries when iterating or dividing ranges. Now, let's focus on how to excel in interviews by leveraging key insights. Recognizing patterns is a critical skill. Many problems follow classic paradigms such as sliding window, dynamic programming, or divide and conquer. Identifying these patterns can help you quickly zero in on an efficient solution. Another important consideration is the trade-off between time and space complexity. For example, dynamic programming can often speed up your solution but might require significant memory. On the other hand, a greedy approach may use less memory but could fail to find the optimal answer. It's also crucial to clarify any ambiguous requirements with your interviewer. Details like whether duplicates are allowed or how to handle negative numbers can significantly influence your solution. As you code, test iteratively. Verifying each part of your solution with simple examples ensures correctness and prevents errors from cascading. Finally, clear communication is key. Even if you're stuck, articulate your thought process. Interviewers value a methodical approach as much as the final answer. To deepen your understanding, it helps to explore related problems that build on similar concepts. For instance, LeetCode 53, maximum subarray, is a classic example of applying Cadon's algorithm to solve a problem efficiently. Then there's LeetCode 70, climbing stairs, which introduces the basics of dynamic programming. LeetCode 322, coin change, combines dynamic programming with backtracking, requiring careful state management to find the optimal solution. Finally, LeetCode 78, subsets, is an excellent example of recursive backtracking in action. Working through these problems can sharpen your skills in identifying patterns and applying the right techniques to solve complex challenges. Finally, let's consider some alternative approaches that are commonly used in problem solving. Greedy algorithms are often simpler and faster to implement, but they don't always guarantee optimal solutions, as they focus on making the best local choice at each step rather than considering the global picture. Dynamic programming, on the other hand, is highly effective for problems with overlapping subproblems, as it stores intermediate results to avoid redundant calculations. However, it requires careful thought in designing state transitions and managing memory. Divide and conquer is another powerful strategy, especially for problems like merge sort or finding the maximum subarray, where you can break the problem into smaller, independent subproblems. Sliding window techniques are particularly useful for problems involving contiguous subarrays or substrings, allowing you to optimize calculations without relying on brute force. Lastly, if the problem involves sorted inputs or monotonic functions, binary search can be a game changer for finding solutions efficiently in log n time. Each of these approaches has its strengths and is suited to different types of problems, so it's helpful to understand when and how to apply them. Great work! To summarize, we tackled the problem of tiling a rectangle with the fewest squares using recursive backtracking. This approach explores all configurations to find the optimal solution. Key takeaways include the importance of recursion in optimization problems and the value of pruning to improve efficiency. Thanks for watching, and remember to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!